Welcome to this new series of videos that we're going to put together for you guys to go over X-ray inspection for ball grid arrays, QFN, and through-hole vias. But, you know, I've been thinking about it, and before we go and do a deep dive into how to inspect these packages, I thought, you know, we should take a few steps backwards to understand where did all that come from, right? How do we get to the point where we need these really tiny sub-millimeter BGAs to build the devices that we love and we use every day? I thought a great place to start to give a historical perspective of, you know, how we got here is to look at, you know, our museum. So this is in our facility in San Marcos, and we have this small, humble museum of really cool X-ray machines with this, including this shoe fitting machine. So these machines were used in the turn of the century to check for, you know, to see if the brand new shoes you're buying will fit your toes comfortably, right? So crazy, super dangerous machine. They were outlawed in the mid-50s, and most of them got destroyed. So we really like to have a few examples of them right here in our facility. And people usually ask me, like, what is this doing here, right? It's an old radio. How does that fit into X-ray technology? And one thing that, the reason why we have this radio here, because they made and the technology is very similar. These are tubes or valves, depending where you live. And these valves are vacuum sealed devices that are very similar to the devices, the X-ray tubes that we find inside these X-ray machines. So I took this tube out of this radio here, and you can see here in the back, there's a whole bunch of them. This is a very rudimentary circuitry, but it's basically an amplifier and a frequency selector, right? So I took one of these from this radio, and we're going to go upstairs. You know, we have our whiteboard up there so we can understand how this works and how this valve relates to this tube right here, which is an X-ray tube that we got from one of these shoe fitting machines. So let's connect those two things together, and then from this perspective, we're going to understand how this tube gave the idea for engineers to design the billions of transistors we find in our devices today. So let's go upstairs and get some more details. All right, for those of you who have been following our channel, you've seen this drawing before in which it relates to an X-ray tube. We're talking about here a valve or a tube from an old radio, the radio you just saw downstairs. The way it works is similar. Like in the 1800s, people were playing with this sealed vacuum tubes, trying to understand what they're used for. And this one specifically is genius, right? So the way this works, you have a heating element here on the bottom, or a filament, if you will, that generates free electrons by heating up the filament. Those electrons are then attracted by a positive anode. So electrons move into the anode, creating current. Now, the genius thing about these tubes is the addition of a grid, right, or a gate. This grid here allows us to control how much current, how many of these electrons go from the filament to the anode by applying positive or negative voltage, right? So think about it. You can go, or 0 volts or neutral, right? Whatever you want to call it. So you can actually change how much current the anode has based on the voltage on the grid. So think about that. This is an amplifier. It's an amplifier, right? Now, if I go ahead and I put a load and a voltage here, and this can be a separate volt supply right there. By putting a load and putting a voltage here, now I have the ability to control how much current is on the load by changing the voltage in the grid. So a small voltage here can represent a large change that, which is the sheer definition of an amplifier, right? So this, if you think about it, also allows you to gate this current by ones and zeros, right? So this is a very early transistor, right? A transistor is a very similar setup, but an NPN transistor, right? You have your N-doped semiconductor on both sides of the transistor, and you put a positive in between, so negatively doped, so more electrons than holes, more holes than electrons. And what you're doing is essentially the same. We're controlling how much current flows through this transistor, let me call it here, by changing the bias on that base, which is the p-doped junction on the transistor. So very similar devices and drastically different. I mean, my father-in-law was playing with this configuration and materials for transistors in the 50s and 60s and 70s, right? When they were trying to understand how fast you could go with this and how what kind of a range of materials you could get to optimize the speed and power of these transistors. So what happens now is that as time went by, these transistors are getting smaller and smaller and smaller. The first ones you could actually see with a bare eye. Nowadays, you can't see them anymore. There are billions of transistors on a device. And as we started packaging, let's go back in history, right? This is supposed to be a historical perspective. The initial ones, in the early days, I'm talking about the 70s, you could have a device or a package with legs on the sides of the package, right? And then you could go ahead and solder those legs onto a printed circuit board. The devices, the transistors started getting smaller and smaller, started packing more stuff. The circuits got more and more complex. And then people said, we ran out of real estate to put pins so we can access, those little bare die inside the package. So what do you got to do? Well, now we've already occupied both sides. Now let's go ahead and put pads on 4 sides of the package. And they got to a point where we started running out of space again. So by the 80s, Motorola came up with a genius idea of a ball grid array. And the ball grid array is nothing but a package, right? Same old package. You put your bare die here, and the bare die is nothing but millions or billions of these little transistors here. You wire bond, you flip chip your bare die to this lead frame or substrate. And then instead of having pins in the periphery of the package, you end up with solder balls under the package. And you can have hundreds of these tiny little solder balls under the package. And you're going to take the package, you put that onto a printed circuit board. Then you can only imagine the difficulties in putting this on a PCB, because now you can't see those solder balls anymore. And that's why you need an X-ray inspection, because the X-ray inspection will be able to go and see through this lead frame and identify the quality of that solder connection. If it's missing, if it's shorted, if you're having pillow, so if the solder is barely touching the pad and makes contact sometimes, doesn't make contact some other times, if there's coplanarity issues, all these things are only available for discovery using an X-ray machine. So in a way, you can say that the ball grid array, invented by Motorola in the early 80s, the ball grid array, the BGA, was the device that allowed the growth of X-ray inspection systems in the SMT industry, because that's the device that created that single package that everyone uses. And by that, created a whole set of bottom terminated components. So in this series, we're going to be looking at BGA in the next video in more detail, what a good BGA looks like, what a bad BGA looks like, what to look for, how to detect, because there's some interpretation that has to happen there, which is not completely obvious and intuitive. So we're going to go over those details and give you the tips and tricks to really figure out if your BGA assembly is good, bad, or somewhere in between. The other BTC that we talk about all the time. It's almost as hard to put down as a BGA is a QFN. A QFN is a package that looks just like this, but there are no leads, right? So there's a wall here. So let me take this, give you a side view. You're going to have a wall. The PCB is here. The component is here. There's a QFN. And we have to apply proper fillet between the QFN and the PCB. They're challenging because oftentimes there's a big thermal pad right here in the center of the QFN. The thermal pad has to be soldered onto the board, and that QFN pad, if you put too much solder, you might end up with the QFN floating or making bad contact on one side and shorts on the other side. So it's a challenging pack. You're going to go over it and study a little more how to properly do QFN X-ray inspection. And then the third video we're going to go over is on through-hole via X-ray inspection. Through-hole vias are incredibly used still, believe it or not, because of the mechanical stability of through-hole via, right? A through-hole via is, as name suggests, this is a side view of your PCB. It's a side view right here. And you have your through-hole via. It goes through the whole PCB. And we're going to look into putting a pin inside here of a component, right? And then we're going to do an inspection to make sure that with the X-ray machine, you can tell if this through-hole via was completely filled or partially filled or no fill at all. So with X-rays, pretty straightforward to get it done. So recapping, when we went over this video, start with a historical perspective, how it all started, with things like this, which will be essentially one transistor, all the way to how transistors were developing, how they work, similarities to a valve or a tube. And then the next 3 videos, we're going to do a deep dive into 3 very popular electronic packaging, Bogger arrays, QFN, and through-hole vias. If you have any other package you'd like us to go over, just leave it in the comments, and we'll be happy to address them in a future video. Hope you enjoyed, and again, don't forget to subscribe, and I'll see you in the next video. Thanks for watching.